the message that I want to deliver, it's a small message, but it's the fact that suppose we have an action of a group on a compact space, and we want to understand if this action is topologically amenable in the sense of an Antara-Mandel-Laroche. So in principle, we should check that every quasi-invariant probability measure is amenable in the sense of Zimmer. But sometimes, if you have some information about the topology and the dynamics, it could be possible to restrict to certain particular measures and maybe impose something stronger than Zimmer amenability. By the way, so this is more or less the idea behind it. So let me start by recalling something about my mini-course. So at the end of my mini-course, I wanted to understand if SL3Z has this property called the AO property. And we saw that at the end, this particular property is encoded in the measurable dynamics on certain extensions of the Stone-Check boundary of the group. And somebody in the audience asked if this property, the AO property, is equivalent to bi-exactness. And I answered that I don't know the answer, but now I want to start really from this problem. And actually, so what was the problem? The problem was the following. In my talk, I always assume that gamma is a discrete, countable, exact group. So the problem that is an open question is the following. Consider the left-right action of the product of the group with itself on the group. And so this induces an action on the Stone-Check boundary. So we want to understand the following. We have, if this action is amenable, is it equivalent to the fact that the Calchi representation associated to the left and right unitary group representations is weakly contained in the left regular of the product of the group with itself. Now I will remind in a moment what is this Q. By the way, this was the idea that we wanted to compare, one wants to understand if there is an analogy between some dynamical property and some property of a particular unitary group representation. So regularity properties of a unitary group representation versus regularity properties of the dynamics. Now, this, and actually, if you remember the idea that was behind the fact that this can be translated in dynamical properties, it's not really about this particular action, but we can consider in general gamma acting on a countable set X, and you can restrict to when this is transitive. So call this sigma, and so by this I mean just homomorphism from the group to the bijections of the set. So let me fix some notation. So associated to this, we have a unitary group representation, U sigma, from gamma to the unitaries on L2 of X. And we also have an extension of this Stone-Check boundary, Stone-Check compactification. And we can restrict to the Stone-Check boundary. Now, what is this Q? In this framework, Q is the following. Q is just the star homomorphism from B of L2 of X to the Calkin algebra, which is defined as the quotient of B of L2 of X over the compact operator. And so in this more general setting, one could try to understand the following. So the question is it true that the action of gamma on the Stone-Check boundary amenable in the sense of Claire. If and only if Q composition is sigma is temperate. So this is one question that one could try to understand. Of course, in this setting, it's very important that the group is exact. Otherwise, we can just take the left action of the group on itself, and this is always temperate, and this is not amenable. So let's try to see this. And well, it is possible to characterize it. I don't know if it's useful, I think so, but it is possible to give a complete dynamical characterization of this. And as we saw in the previous lectures, in order to understand this, one has to pass to particular extensions of the Stone-Check boundary. Okay, let me recall these just these extensions. So the idea is that this property is encoded in the irregularity properties of Koopman representations associated to quasi-invariant probability measures on certain extensions of the Stone-Check boundary. Now I have to tell you what is the extension, just remind you what are these extensions and what are the probability measures. So the extensions are given, so I will give you the space and the probability. So the extensions are given by the following. We take a free ultrafilter on the natural number. Associated to this, we can consider the following equivariant map into the ultraproduct C-star algebra. Just to recall you, this is just the infinite product over the natural numbers over a particular ideal, where the ideal is just the sequences of functions, such that the norm goes to 0 with respect to omega. So this is just, it's like you are taking all these sequences and you are looking just at the behavior at infinity with respect to this ultrafilter. So we have, this is gamma equivariant when we give to this the diagonal action. And so associated to this, we have a gamma equivariant surjective map, continuous map, from the spectrum of this to the Stone-Check compactification. And the space I want to give you is this extension. I call it delta beta omega x. And this is by definition the inverse image of the Stone-Check boundary. And actually it's just a Gelfand duality that gamma equivariantly, this is the continuous functions on this are the same as the quotient of the ultraproduct over the ideal generated by C0 of x when you embed diagonal. So this is just Gelfand duality. Okay, so this is the space. So what are the measures? The measures are given by the following. So we start, so we have this omega, and we take psi n, a sequence in L2 of x of norm 1, and now we suppose that psi n goes to 0 weakly with respect to the ultrafilter, and now we modify a little bit this sequence. So we take a sequence alpha I in L1 of n, or norm 1 if you want, such that all these are positive, and instead of considering psi n, we consider the sum over I alpha n psi n of sigma of gamma I to the minus 1, so composition, over the norm of this. Okay, so here I mean that gamma I is an enumeration of gamma with gamma 0 that is the identity. Okay, so I call this psi n tilde, and the point is now that this sequence induces a probability measure on this space on the space that I constructed, and the probability measure is given by the following. Take f, a continuous function here, and take a representative f in n inferior of x omega such that f plus this ideal is equal to f, and the probability measure is just the one given by the following. Psi until distance f to the limit along omega of this capital F psi n tilde psi n tilde. Now the point of perturbing this sequence is the fact that now this probability measure is gamma quasi invariant. Okay, and I denote all the measures that we can obtain in this way as Calkin measures. I call them Calkin measures. And I denote the set like P, Q, delta, beta, omega. Okay. So now what we saw is that if we want to understand this condition, is equivalent to the fact that all the Calkin measures give Koopman representations which are temperate. So let me, where is this? So let me as a theorem, if you want. So we are in the following situation. We have, this is the Stonechek boundary of X, and we have all this very large cloud of extensions, each given by a free ultrafilter over the natural number. Attached to each of these extensions, we have probability measures. Quasi invariant probability measures. And now what is the point? The point is the following, that so Q composition U sigma is tempered if and only if for every mu and for every omega in un ultrafilter over the natural number, for every mu a Calkin measure on the associated extension, pi mu is tempered. So this is okay, a characterization of this property. So the reason why I was interested in this characterization is that maybe one can use geometry. But okay, let me just say this. And what is amenability on the boundary? This is equivalent to the fact that for every mu a quasi invariant probability measure, so for every omega free ultrafilter, for every mu a quasi invariant probability measure on the associated extension, we have the following. We have that pi mu is tempered, and a second property that is this pair amenability that was defined by Zimmer. It's the fact that there exists a gamma equivariant conditional expectation from L infinity of mu times mu to L infinity of mu. So okay, this is just I wanted to introduce this characterization. Now, if you look at this, so at the end the idea behind this is that both properties are properties of particular extensions of the dynamics on these extensions on the boundaries. But what I want to say is that what is really this property? So this property is actually telling us that every measure on every of these extensions is amenable in the sense of Zimmer. And so what is telling us is that the action of gamma on this extension is topologically amenable. So it's amenable in the sense of Claire. This is really what this property is telling us. So why can we characterize amenability on this space by looking at these extensions? The reason is that these maps, psi omega, are amenable. So an amenable map means that whenever you have topological amenability on this extension, you automatically have topological amenability on the factor. Why is it? The reason for so is this, and then one is the psi omega is amenable. So in particular, it is enough to find, if it's easier, but it's enough to find a particular free ultrafilter for which we know that the action is topologically amenable. So now, why is this true? The reason lies behind.
What does this mean? The amenability of this map.
It means.
You define this.
No, I didn't define it. But
I didn't define it neither.
No, what I mean is that if the action is topological, a map is amenable. If you want, if the action is amenable here, implies that it's amenable on the factor.
Okay.
This is what I mean.
That's
In general, you have the converse, but in this particular case, you also have the. I mean, if an action is amenable here, it's automatically amenable on every extension.
Yes.
But in this particular case, these extensions are, and this, you see, this is a sort of paradigm. When you study the Calkin algebra, or you study something that is so complicated, like the stone-check boundary, in some sense, there is always this paradigm that there is enough space to encode inside this space some extensions, up to a certain level. So what I want to say is that in order to check amenability here, it's enough to pick your favorite extension and check amenability there. Why is this true? So this is based on a no standard version of a proposition by Osawa. So Osawa understood the following, that under this all this structure, all this hypothesis, we have the following. So the action of gamma on the stone-check boundary of this set is amenable, is equivalent to the fact that there exists a nuclear UCP map from the reduced group C-star algebra to the bounded operators on H2 of X, such that, so let's call it phi, such that phi of lambda gamma minus U sigma of gamma is a compact operator. So this was one thing that Osawa understood in his paper on what was Kurosh-type theorem for two-one factors. So now the point is that it is possible to give a sort of no standard analog of this. So we pass to these extensions, and what we can see is the following. That one, so let us fix a free ultrafilter over the natural numbers. So what is equivalent is that the action of gamma on the associated extension is amenable. And now we have an analog of this nuclear UCP map. There exists a nuclear UCP map from, let's call it phi omega, from the reduced group C-star algebra to something like a non-standard version of the bounded operators, such that phi omega of lambda gamma minus u, let's call it u sigma omega of gamma, is in a non-standard version of the compact operators. So, and this is actually equivalent by modifying this to the fact that the action of gamma on delta beta x is amenable. So this is just to state this. Now I have to tell you what is this, what are these objects. But these objects are defined in the following way. So we have a diagonal embedding of B of L2 of x inside the ultra product. And so in particular, we can embed finite dimensional projections, let's call them Pn, in this ultra product of B of L2 of x, the C-star algebraic one, for every n. And so we can take the union and we close in the norm of the ultra product. So this is the analog, this standard analog of the compact operators. What is this? This is the multiplier algebra of this inside this ultra product. So this is the multiplier of this inside the ultra product. Okay, now we have all the characters, all the ingredients. So what is the multiplier algebra? It's the largest possible unital C-star algebra that contains this as an idea. This always exists. So okay, now what is now the point? The point is that we are given this action of the group on this countable set, and we want to find this nuclear UCP map. And in order to find this nuclear UCP map, we will see that we will use the dynamics and we will use Koopman representations to construct this map. This is what I want to say. So the goal now is to construct this particular map, imposing some restrictions. Okay, so let's see. So in order to do this, we need to look a little bit, some information on the topology of these spaces. So here it's a technical assumption, but I suppose that omega is a non-trivial ultrafilter. This just means that you have a countable family of subsets of this ultrafilter whose intersection is empty. And you always have this in the natural numbers. Okay, so now we consider the following. This is the non-standard model of X associated to omega. This was defined by Robinson in his book. The book on non-standard analysis. And then this is the following. He denotes this like this, and this is defined as the following. The sequences in X modulo a certain equivalence relation, where the equivalence relation is given by the following. Xn is equivalent to Yn if they're equivalent along the ultrafilter. So this means that there exists an element of the ultrafilter such that Xn equals Yn for every n in A. Okay, so this is just to recall the construction of the non-standard model associated to extend the ultrafilter. And now there is the part at infinity of the non-standard model. So part at infinity part. And this is just defined by the following. We take all the elements of this non-standard model such that xn goes to infinity along omega. So this means, so pick a representative of this class. This means that for every finite set in X, the ends for which xn lands outside this finite set is an element of the ultrafilter. And it's easy to see that this does not depend on xn. Any xn in the same class will give the same. So this is well defined, and this is the part at infinity of this non-standard model. Now, what is the point? Is that this embeds inside these extensions. So there is a natural embedding of this gamma equivariant. Here we have an action that is just pointwise. It's for every gamma acts pointwise on the sequence. And this is embedded in this extension. And the image of this, so the embedding is just given by the natural one. I mean, we take a f, a continuous function, such that f is equal to f plus I of C0 of x, and so the character associated to xn omega is the limit along omega of this. So it's f of x. Okay, so we have this natural embedding, and the point is that the image, this is inside this, is discrete, open, and dense. So in particular, if you want this space is a gamma equivariant compactification of the part at infinity of the non-standard model. Okay, so we have this. And now I want to do the following. So we are in this situation. We have this is the space. We have all these points that are the non-standard model, the part at infinity. And now I want to consider particular quasi-invariant measures on this space. And these measures are just the measures supported on orbits. So we take an orbit. And this will give I can take a Kubma representation which gives a positive mass to every point of this orbit, and I can take also the convex hull of these particular measures, and I can take the Kubma representations associated. So in this way, I obtain a particular set of measures and associated Kubma representations. And actually, it's a fact that all these measures are Calkin measures. So these are okay. So basically we are considering this set A, that is the convex hull of this particular probability measures supported on orbits in the non-standard model. Okay, so this set has some particular properties. First of all, if you have mu that is below mu in the sense of absolute continuity. Then there exists star homomorphism, surjective star homomorphism, from what? We can take pi mu. This is the Koopman representation, and we can see this as a representation of the full cross product sister algebra. So I can consider this as a representation of this ultra product, cross product gamma, to pi mu of the same. And okay, so this is one property. Another property is that for every mu, there exists another measure, let's call it theta, such that mu is less than theta, and also nu is less than theta, and theta is again in A, it's clear. And but there is also something more that is important. It's the fact that for every mu in this particular set of representations, actually it's much more general. This was observed by Edwin and Lee, that pi mu, so when you restrict pi mu to the commutative algebra, this is just the GNS construction. So this is dense in L infinity, but it's actually equal, it's surjective. So this is L infinity of mu. And these maps under, when we we don't need to restrict these maps. So what is this star homomorphism? Well, this is given really by the fact that if you have mu that is inside nu, you have the radon-Nikodym derivative. You take so you have this, and this implements an isometry between the two Hilbert spaces, and this is just given by this isometry. So it's weakly continuous in particular. So we are in this situation, sigma weakly. We are in this situation, and now what can you do with this situation? So this is all the way to construct this UCP map. In this situation, we can do the following. So let's proposition. Before the proposition. So we have all these particular representations, and now I can define a representation that I call it pi A from this cross product to, if you want, the bounded operators on the direct sum of all the measures here. And this is given by the inverse limit of these representations. So what is the inverse limit? So you see, if we take, we can define pi A of L infinity x omega cross gamma. What is this? This is a subalgebra of the product of all these measures, pi mu of this algebra. And this is given by as a set, as the sequences f mu, such that f mu equals, so call this pi mu mu. So f mu equals pi mu of f mu for every mu less or equal than mu. So this is a general construction in sister algebras. You have this index set, and you can take the inverse limit. So this defines a representation that is just given by localizing at every measure, and it respects this. It lands inside this. So now the point is the following. Suppose that the action of gamma on this the action of gamma on the part at infinity of the non-standard model is amenable. So this means that the stabilizer of every point is amenable. Stabilizer in gamma for every point. And then what I tell you is that then there exists a gamma equivariant UCP map from L infinity of gamma to this particular C-star algebra. To actually the restriction to the, we can take pi A of the commutative algebra. So this is really the important fact about this. So how can we see this? Well, the idea is the following, that now the point is this, that every of these, when we take just, so for every mu, pi mu of L infinity of x omega is a von Neumann algebra. So here, when we restrict just to the GNSs of the commutative algebra, this is a von Neumann algebra. The product is a von Neumann algebra. Now, since the stabilizers are amenable, since we have the action of gamma on this set is amenable, then it's possible to see that every of these measures is Zimmer amenable, and this means exactly that there exists, for every mu, there exists a gamma equivariant UCP map from L infinity of gamma to pi mu of L infinity x omega. But then we use the fact that here, when we take just the GNS constructions associated to the commutative algebras, the product is a von Neumann algebra. So, how we use it? Well, you see, we have all these measures. Now we take a finite subset of measures, and we have the following. Now, on this finite subset of measures, we can find a maximal element. On this maximal element, we have, so let's call, I don't know, pi mu of L infinity x omega. We have a gamma equivariant UCP map from L infinity of gamma to this, and we can push it on all the other measures which are smaller than this, using this weakly continuous star homomorphism. And so at the end we have a net indexed by the finite subsets of measures. So we have outside we just take any UCP gamma equivariant map from L infinity of gamma to pi nu of this algebra. Okay, so we have a net of UCP maps which go from L infinity of gamma to the product of the GNSs. Since this is a von Neumann algebra, this net, if we take a cluster point, the space of these maps is compact with respect to the point weak star topology. And so we can take a cluster point. And now one has to check that whenever we take, so call these maps, I don't know, phi f, indexed by the finite subsets. So when we take a cluster point of this map, cluster point, one has to check that the image of phi, so the range of phi, is inside the inverse limit. So restricted to this commutative algebra. Okay, so this is the main ingredient. So here we really needed the fact that the GNSs are surjective on L-infinity. Okay, so at this point, what do we obtain? So, there is one last bit, that is the fact that since all these measures, as I told you, are calculus measures, actually every of these Kubma representations factor through the embedding into this algebra. So since every mu in A is calculus, then for every mu in A, pi mu from L-infinity of x omega cross gamma to the associated Kubma representation factors through the map, the star homomorphism, that sends this to the C-star algebra generated by this commutative algebra and the group. And this is inside this non-standard version of the bounded operators. Okay, this is really the last bit. Now, what can you do with this? Well, we know that there is, so at the end we are in the following position. We have this C-star algebra, that is inside this algebra that we are interested in. So this is represented with this pi A. So let's call it just pi A of this, okay? Now this contains pi A of the commutative algebra. And, okay, so we know from that if you assume that the stabilizers of points in the non-standard model are amenable, then we have gamma equivalent UCP map here. So we have this. Okay, now if you have a gamma equivalent UCP map, you can always extend to a UCP map from the full group, from the full cross product to the C-star algebra generated by this and the group. So extend to this cross product gamma to the C-star algebra, this C-star algebra, and this extension actually is such that it sends the unitary here to the unitary here. Now, since the group is exact, the full group, this C-star algebra is equals the reduced cross product and is also nuclear. So at the end I can put reduced here, and this UCP map will send lambda of gamma to the unitary that is here. So pi A of sigma omega. Okay, this is all we need. Now, this particular map, so here we have the reduced group C-star algebra. So this map is a nuclear UCP map, since this algebra is nuclear. So this is, we obtain this nuclear UCP map. And since this is nuclear, we can use Choi-Efros lifting, and we can extend this to a map that goes here. So here we obtain a map phi omega that is nuclear and UCP. Okay, and this is our candidate. So at the end, what we obtain is at least a UCP nuclear map from the reduced group C-star algebra to this particular C-star algebra that we are interested in. Now the point is that we would like to have this other condition, that the difference between applying a group element, viewing a group element under this UCP map, and viewing a group element as naturally acting on this C-star algebra, the difference should be this type of compact operator. Okay, so now we have to impose some other conditions. This is the point. So at the end, just to stress, it's all very technical, but just to stress the idea. The idea is that we can translate this amenability in the existence of particular UCP maps, and we can employ properties of the dynamics. For example, here we have used the fact that the genus constructions are surjective in L infinity, and we have used amenability of the stabilizers of certain points in order to construct candidates for this map. So this is where the dynamics takes place. So now what we can see. So by the way, observe the following, that so now we have this UCP map. Now if we follow one group element, so take gamma, we send gamma here, and we want to check, we want to understand what is the difference between this and this. So you see, I tell you that the difference is always in the kernel of this. Why? Well, because this is an extension, right? So this UCP map was defined in such a way that the group element is sent exactly to the image of the group element here under pi a. So if we take the extension, we look here, we take. So what I'm saying is that if we take phi omega of lambda gamma minus sigma, the element represented here, when we apply pi a, it's 0. So this is always in the kernel. So at the end, what we really want is some condition on the dynamics which ensure that the kernel is contained here. This is at the end the story. So we can do it in the following way. So now we have to be a bit careful. We restrict to particular cases. So now suppose that gamma has the AP property by Hagerup and Kruse. And suppose also, so now it's not enough to consider amenable stabilizers. We have to consider trivial stabilizers. So suppose gamma acting on X is almost free in the sense of Yair. By this I mean that if you take, for every gamma, the stabilizer, so the fixed points have finite cardinality. This is what I mean. I think this agrees with your definition. Yeah. So I want this. So if we have this, then the action of gamma on the Stone-Check boundary of X is a minimum. This is what we want to achieve. So first of all, observe the following, that by this property, then the action of gamma on the infinite part of the non-standard model is free. And this is very easy to see, because So just it's trivial. If gamma xn omega equals xn omega, this means exactly that there exists a subset in the ultrafilter such that gamma xn equals xn for every n in A, but the ultrafilter is free, and so every subset is infinite. And so this is just this. Okay, so this action is free. And now we just have to use the AP property. So suppose, okay, so suppose we have F in the sister algebra generated by this commutative algebra and the group that is inside here. And okay, so suppose now that what I want to say is okay, yeah. So suppose now that so F by AP property we can write F is the limit over a certain index set I of what? Phi I of a sum over gamma of phi I of gamma F gamma U sigma omega of gamma. So the AP property basically guarantees that when you approximate, so these are finitely supported functions with pointwise go to the identity, and the AP property guarantees that whenever basically that you can choose F gamma uniformly. This is the point. So now suppose that pi what to sorry, 1 second. We want to check that the kernel of pi A is contained there. Yes. So suppose that pi A of F is equal to 0 and there exists let's call it gamma tilde, such that F gamma tilde is not in this particular sister algebra. But so this F gamma tilde is in L infinity of X omega, and so being here means exactly that it should be in the ideal generated by C0 of X. So the fact that this is not in this means, so you see the picture is the following. We have, this is the spectrum of L infinity of X omega. This is, we have this gamma equivalent quotient. This is the open set associated to the ideal I C0 of X. Here we have this extension of the boundary, and here we have this dense set of points which constitute the part at infinity of the non-standard model. So, what I'm saying is that if this is not in this ideal, so let me equivalently. If this is not in this ideal, it means that under this the natural surjective map, this should give a function that is not zero on this set. And so since this set is dense, there should be at least one point here, let's call it xn omega, such that this function evaluated in this point is different from zero. Okay, so now we just have to put the things together. Yeah, but I'm almost finished. So we put the things together, and what we have. So you see, since these are calculation measures, but it's very easy to see. We have basically measures supported on discrete sets, countable sets, and so there exists psi. So if this is not here, I can take. So I want to evaluate this: the limit on n that goes to omega of f, so this, yes, f delta, let's say xn omega, yn omega, and gamma tilde okay, I want to evaluate this. Now, the point is that this is, so yn omega defined to be, let me think, no, I take xn omega, okay. So, since we have AP property, this is basically approximated, so this should be the limit of all this sum, so gamma, phi I of gamma, f gamma, u sigma omega of gamma, applied to this. So now, if this is different from zero, what we obtain is that now we try to compute this, we approximate this up to an epsilon that is very small, and so we are taking a finite subset, and now taking a finite subset, you see that whenever I take the sum, now I can suppose that phi I of gamma is very close to 1, so this becomes delta gamma xn omega, delta gamma xn omega, gamma tilde. So since the action, we saw that the action here is almost free, and so this action on this set is free. Whenever I take this scalar product, this is only the scalar product up to phi I gamma, okay? Gamma tilde is the scalar product f gamma tilde delta and so now I see that I should have taken, instead of xn, yn, that is gamma tilde to the minus 1 of xn. Okay, the point is that this will give just the character associated to Xn omega to F gamma 0. So what we saw is that we have, we realize this is different from 0, but this comes from a Koopman representation. Supported on the orbit of this particular character. And so what we found is a Koopman representation which comes from the set that we defined, for which this function goes to something that is not 0. So it's impossible, what we are saying is that it's impossible to have a function for which all these coefficients are outside the ideal generated by C0 of x, and such that this is in the kernel of this. So this implies, this means exactly that the kernel of this so the kernel of this particular representation is contained in what? In the sister algebra generated by the ideal and the group. But now the group is inside the multiplier of this ideal, and so this is contained in our beautiful sister algebra. So this basically finishes the proof of this result. And now so this is more general than just free group action, but it's so corollary. Yes, just the corollary. So just to state the result in the title. So corollary. If you take n, m greater or equal than 2, whenever you look at the action of F, the free group on m plus m generators, on the quotient by Fn, you look at the stone check boundary, this is amenable, and using the result by Cirbecca and Callender, in particular, we obtained that the sister algebra of this representation of the quasi-regular, so let's call it gamma, and let's call this lambda, as a unique idea. That is the compact operator. Okay, I stop.
So, questions? I wonder, so you have some extension of the cross product, which is, I guess you get, which is equivariant, right? So, by the compacts.
Where do you mean? Here?
Before you had like some drawings in that, in the second part of the left board that you have erased. But you get extensions also. Do you get extensions also of the cross products?
Yes.
Yes. By the compacts. These by these beautiful algebras you said.
Yeah.
Okay. Which is equivariant.
Yeah.
Right? So have you also considered like the opposite algebra, the cross product? Acting on that? And And the question would be, would these two representations of the actual cross product and the opposite one commute modulo compacts?
I don't know.
Because in philosophy, philosophically, something like that could happen like for hyperbolic groups. If you act on like Gromov boundaries, and then you are into a good position to do some index theoretic applications with extensions that you build.
Yeah, I don't know if one can go farther than what you said. I mean, yeah, probably.
Because you have the extensions already.
Yeah.
You have built them. So the question I have is like whether these two will commute modulo this algebra.
Yeah, it's something I should think about.
Usually, like for the hyperbolic groups at least, it's not an easy. I mean, you use the dynamics.
Yeah.
Something that.
Yeah, I don't know. I should think.
Other questions?
So I did not, I was not able to follow the details, but as far as the truth,
I suggest you take the coffee break, and then you can talk.
okay. Can do it.
Okay. I mean, people want coffee, so.